The moon is moving away from Earth right now. Not in theory, not as a metaphor. At this exact moment, the moon is farther from Earth than it was a year ago, and closer than it will be next year. 1.5 inches per year, measured to millimeter precision since 1969, when Apollo astronauts left mirrors on the surface and NASA started firing lasers at them from Earth. The time it takes the laser to make the round trip reveals the distance to within 3 centimeters. The data is real, verified. NASA confirms it, but here's what almost nobody mentions. That rate shouldn't be this high. The models predict a slower drift, and the gap between what we measure and what the models predict points to something about Earth and Moon's shared history that we still don't completely understand. 3 questions. How do we know with such precision that the Moon is drifting, and how accurate is that measurement? Why doesn't the current drift rate fit the models? And what does that say about the past, and the consequence that is real even if it isn't immediate? What changes on Earth as the Moon moves away? Stay until the end. The last consequence isn't the most obvious one, and it's the one that changes the way you look at the Moon every night. The experiment that confirmed it started with an aluminum box the size of a carry-on suitcase. On July 21, 1969, Neil Armstrong placed a panel covered with 100 fused quartz prisms on the lunar surface, designed to do one thing: send light back exactly where it came from. They called it a retroreflector, the first permanent scientific instrument ever placed on the Moon. Since then, observatories in California, France, Italy, and Apache Point in New Mexico have been firing laser pulses at that panel, and at the ones left by Apollo 14 and Apollo 15. Light travels at 300,000 kilometers per second. The round trip takes about 2.5 seconds. Measuring that time to nanosecond precision gives scientists the distance to the Moon, accurate to within 3 centimeters. 3 centimeters at 384,000 kilometers. Decades of those measurements confirm the same thing. The Moon drifts away 3.8 centimeters, about 1.5 inches, every year. Not an estimate, one of the most verified data points in all of planetary science. But here's where the real problem starts. Because when scientists took that rate and ran it backward in time, what they found didn't add up. Get this, if the Moon had always been drifting at 3.8 centimeters per year, just 5 billion years ago, it would have been so close to Earth that tidal forces would have torn it apart. The Roche limit, the minimum distance at which a satellite can orbit without being destroyed by the planet's gravity, would have been crossed at a point that's geologically recent. But the Moon is 4.5 billion years old, and geological evidence shows it's been orbiting stably the entire time. The current rate is not the historical rate, and that gap is the real mystery. Geological records confirm it. Ancient marine sediments, called tidal rhythmites, layers of sediment deposited by tides in daily and monthly cycles, let geologists read tidal patterns from hundreds of millions of years ago, the same way a tree shows its rings. Those records show the Moon was drifting significantly more slowly in the past. The drift rate hasn't been constant. It varies with continental configuration. When the continents were distributed differently, tidal friction between the ocean and the seafloor was different, and that changed how fast the Moon moved away. The current rate of 3.8 centimeters per year is anomalously high compared to the historical average. Modern Earth's oceans, with their specific arrangement of continents and basins, are accelerating the process more than was typical for most of Earth's history. In other words, the Moon is leaving faster than expected because modern Earth is unusually efficient at transferring rotational energy into the Moon's orbit. And that's what the models didn't fully predict. If this is changing what you thought you knew, hit like. It helps more people find this. Now, the question that actually matters. What changes on Earth as the Moon moves away? First, the day gets longer. The energy pushing the Moon outward comes from Earth's rotation. Tidal friction acts as a brake. The Earth day lengthens by roughly 1.4 milliseconds per century, imperceptible in a human lifetime. But accumulated over millions of years, it's enormous. 1.4 billion years ago, A day on Earth lasted 18 hours. Ancient coral records confirm it. Second, the tides change. The moon is the primary driver of ocean tides. As it moves away, its gravitational pull on the oceans decreases. Tides weaken. The mixing of water between deep and surface layers, which feeds phytoplankton and regulates oceanic oxygen, gradually diminishes. Third, and this is the one almost nobody mentions, Earth's axis starts to destabilize. Lunar gravity acts as a stabilizer for Earth's rotational axis. Without that influence, models published by Jacques Lasker in Nature in 1993 show the axis could oscillate chaotically between 0 and 85 degrees over millions of years. Mars, without a large moon, is the example. Its axis swings between 10 and 60 degrees, and there's evidence that instability contributed to the loss of its surface water. When does this become a problem? On scales of hundreds of millions to billions of years. Not tomorrow, not next century, but there's something more immediate that the models point to. In roughly 600 million years, the moon will be far enough away that total solar eclipses will no longer be possible. The perfect coincidence, the moon covering the sun exactly, is temporary. On a cosmic timescale, it's almost over. And the current rate, higher than the historical average, means that moment arrives sooner than earlier models predicted. Now, something I want you to think about before this video ends. There's a question geophysicists haven't fully closed. If the drift rate varies with continental configuration, can human activity, through changes in the oceans, affect that rate in any way? Climate change is altering the distribution of water across oceans and polar ice caps. Redistributed water changes Earth's rotational inertia. That inertia affects tidal friction. The influence would be minuscule, but the question is legitimate, and nobody has answered it with definitive data yet. What do you think? Write in the comments. Natural. If you think the moon's drift is purely a natural process independent of anything happening on Earth, or connected. If you think changes on Earth can influence the lunar orbit in some way, even minimally. One word. Tell me in one line why you chose it. If these are the questions that keep you up at night, this channel is for you. Subscribe so the next video comes straight to you. Because next week, we're connecting the moon's drift to what's buried under its surface, and to why 2028 might be the year we finally understand what's happening inside.